first I'd like to thank the university, especially President Huang, for inviting me to this very important and interesting forum and to give a lecture here. This is really my great honor to be here together with Dr. Benoit. You know, because of him, I have been really enjoying life for the last 25 years. Okay, and he creates such a wonderful arena so we can work on. Okay, and we have heard many the talk by Dr. Benoit about the potential technology aspect of the high temperature superconductivity and the recent development, and really a great promising that superconductivity will be really the key component in the future as related to our energy issue and others. Okay, but I am going to give a little bit different content in my talk, more from the material development for superconductivity. So I'm really talking about some of the recent development in superconductor, especially there is a new series of the material discovered 20 years after the copper oxide was discovered by Dr. Benoit and Mueller. Okay, so I'm using this title from Bronze Age. We all know bronze is basically copper base, and then we are moving to the Iron Age. Okay, you see the detail, right? So I think it's nice that after Dr. Benoit's talk, I can skip many biographs. For example, we know that this year is the 100th anniversary of superconductivity. You know, the community really very, very exciting and happy that we have this 100-year to celebrate. Probably most of the audience already know, okay, but let me just mention there's a very important development after about 50 years that BCS, you know, Badin Cooper Schrieffer, the theorists, develop a picture to understand what is the fundamental physics for superconductivity. So the so-called the BCS theory, okay? I'm not going to go through the detail because today is not an occasion for that. But the main thing is that to be a superconductor, then you require that the electron is no longer moving individually. It has to be formed into some kind of pair, right? Which means the two electrons were moving coherently together as so you have a new quantum state, different from the individual electron. Well, I like one of the very amazing artwork. Okay, this is a painting by one of very famous Chinese painter called Wu Zuoren. Okay, is a very famous artist. But the whole ideas came from Li Zhendao. Okay, the Nobel TDD, the Nobel laureate who discovered this parity variation. And so this could be a picture of two electrons forming into a pair, right? Although this is a schematic or ideally, which means that the two electrons form into a very nice coherent state. And the picture is very nice. And when the two electrons form into a pair, then quantum mechanics will show that there are some interesting follow-up, which means this is another picture showing that what is it? One time people are working very seriously on this, the carbon-60, because that will become superconductor if you have some electron doping to the system. And this Chinese, I think most of you can read it. It said the single electron will meet a resistance, so it's very hard to move around. But when you become pair, then it fly, okay, like a butterfly, right? Okay, so 就是单行苦分异阻力双节生次就成超导. So you have a two electron forming to pair, then you become no resistance at all. Okay. So this is just two very beautiful pictures to show the major content. To be a superconductor, you need to have a pair electron and then form into coherent state. That was the basic content of the BTS theory. But after 1957, the BTS theory was developed, and there was a very important relation that physicists or chemists can follow in terms of understanding the fundamental of superconductivity, and also can become a good guideline in terms of the searching superconductor, particularly related to some of the fundamental parameters, like the superconducting transition temperature, the TC. It can be related to some kind of energy. And here, without going into detail, okay, this is some electron phonon, the lattice vibration frequency, and those are the parameters of the material related to the density state of the electron and the electron phonon interaction strength. Okay, so if you look at this mathematical relation, that you can tell, if we want to have some TC higher, the temperature higher and higher, you want to have this number high, right, large. There's a very simple linear relation here. And you also like to have this parameter larger, because this is exponential minus. So as it become larger, this factor becomes smaller, and that factor becomes smaller. So you have a larger TC. Okay, so that became a very important criterion in the late 50 and 60 people when they tried to find a new material. And Dr. Bernard already mentioned, in order to have a good application or realize the practical application of a superconductor, you need to overcome some parameter, the temperature, the magnetic field, and the so-called current density. Okay, so there are something that we need to overcome. And in order to do that, if you have a higher TC, certainly it will go together. The JC may all go up. Okay, in principle. So as mentioned, also since the discovery in 1911 by Onnes, well, this is one of the major efforts in community, including, I think, both physicists, chemists, or material scientists try to find a new material. But the advancement was very slow. Okay, for 3/4 of a century, this is only 20-degree increase. Okay. At that time, actually, I was a student, so people saying, well, if we want to go to hit this a boundary, the barrier of the liquid nitrogen, you take a 200 years. If you take the linear extrapolation, okay, 就你线性把它扩增的话 to reach that point will be 200 years, require 200 years. So a lot of people has no hope. But as Dr. Meno mentioned, the real discovery comes from one that believed nothing impossible, right? So when I was a student, I was still thinking there's a potential, because there are many interesting ideas behind. Let me just mention a few things, okay? For example, if we look at this equation here, right? This energy can be different, right? If I can somewhat change in this parameter, then the TC can be high. And also, of course, you can also do something to modify. And the exact content of that, although BCS theory tell you is the so-called electron phonon, the lattice vibration, the atomic vibration, which is important. But the detail of that, the so-called exchange, is not that critical, okay, based on this equation. So this omega d can be something else. Right. That's why in the 60s, in physics community, there were a couple of proposals. For example, this is the Ginsburg from Russia who got a Nobel Prize in 2000 for his major work in Ginzburg-Landau equation. And he mentioned that might be some kind of two-dimensional metal semiconductor sandwich structure, that you have a metal insulator, metal semiconductor, okay? Then it's possible to lead to high TC. And this is William Little, a professor at Stanford University, also mentioned that you can use a organic long-chain molecule. It become metal, and then it could be possible. So some theoretical argument show the high TC. And even in 1973, Bardeen and his postdoc and student, similar idea of the Ginzburg, also mentioned there's some kind of interface superconductivity. I mentioned it because this is a subject that I was working when this is just give you the background of paper. Okay. For example, this particular so-called ABB model, the Bardeen, Allender, and Bray, proposed in '73. At that time, I was a graduate student back still in Taiwan. So I was interested in the superconductivity, so I was following the paper. This is the theoretical work, so I did a little bit theoretical to follow up and to see, well, that's interesting. If somehow we can accomplish this, then maybe there's a possibility, okay? So fortunately, after I graduated and decided to move to the state, and I joined Professor Paul Chu's group in Houston in 1977. And without going into detail, I show you that we did a few work at that time on the so-called interesting, the Chauvel phase, which is also discovered by great chemists, French chemist Chauvel. There are many interesting physics, and because there's interesting magnetism and superconductivity. But I was managing in 1980 to find, this is the, I was a student, but I did most of the measurements and the material. And we found that we can make a non-superconducting material by using pressure, okay, and make it a superconductor, right? So that was one of explanation in our paper. It sort of quote that kind of metal insulator boundary, okay? So there's a potential that has something to do with it. That was a long time ago. And later on, and this is the data I show that in that particular paper. And about the time I finished my PhD degree, I was starting working on the oxide. I believe probably this is also the same time Dr. Mueller and you were maybe on this perovskite, because it used to be a very important system for ferroelectric type. But that was a system discovered by a chemist, again, in 1976, showing very interesting superconductivity. Right? So that leads us to believe that maybe oxide is another really a direction we should go. Although we spent some time, didn't get much improvement, but we did also find there are some interesting relation between the metal semiconductor phase transition and so on. So that's also back to the idea of the metal semiconductor interface. Seem to be working very well. Okay. And after I finished my degree, working a few years, and we even think, if you want to make it this kind of metal insulator material, you want to have a perfect matching between metal and insulator. So, the search is something could come related to such kind of direction. And I got an offer and work in Alabama, Huntsville. And because there is a very interesting facility in Huntsville, Alabama. Right? It has a building about 100 meters tall. because this is the NASA research center. And this building was constructed so that a space shuttle or rocket can put into this structure and then shake it with a very high speed or a very strong force, which is really to test the mechanical property of the rocket or the shuttle. Because when you launch, you have to sustain a very vibrant mechanical strength. Okay, so the whole building was constructed for that purpose. So there's a very big vibrator in the ground and so on. Well, but because it's 100 meters, so there's a 7 second if you free fall from the top to ground, right? And which means you can have something drop in the melt and then solidify in the ground with 7 seconds. And that allow you have a 7 seconds without any gravity. All right. Now let's think about it. No gravity means that, right? The two material that has a different density can have a almost perfect mixing, right? With the gravity, normally you will separate for two very different if they don't mix together, right? That's why, for people, student here, why the oil and water would not mix. You always see water floating on the top of, the oil always floating on the top of water because the density of water and the oil are different. The 水跟油不混 because of gravity. But if you mix them in a zero gravity environment, then you have almost perfect mixing. Okay, so we was just crazy, thinking, well, maybe we can do that, so you can have a perfect mixing between metal insulator, metal semiconductor with a very nice interface. Okay, and that was also a dream to push for better superconductor and to sort of maybe we can demonstrate some of the idea, follow the theoretical proposal. So that I was working for that. That was from '84 to about '86. And then the great news came in '86, right? After 75 years, Dr. Benno Mueller, as you already heard, in '86, they announced this great, published this great paper. And of course, during the time when I was working in Huntsville, I still keep a very close interaction with Professor Chu in Houston. We still collaborate, pushing, actually searching for new material and so on. So when this paper came out, Professor Chu, of course, right after and immediately moved into the system and used the high pressure technique to investigate what the effect to the property, okay? And as you probably know that he found with a little bit of pressure, the TC goes up and higher then goes down, and so they go through a maximum. By the end of 1986, I was in Huntsville, so I and Professor Chu have agreement. So he still continue working with the pressure, and I start to look at the chemical way by using so-called chemical pressure, by substitute different elements and to see how it would that affect. Okay, and so we sort of divide our efforts and push it. And this is what Dr. Benno mentioned. The rally really started. Okay, from 1988 and 1986. And by that time, we already know what the structure of this, the so-called Zurich perovskite, okay? And this is the different representation. There's the octahedron with the copper in the center, but it's still a so-called perovskite structure, okay? Although it's somewhat distorted. This is the ideal case. But if we can distort it, it still have this perovskite structure. And this kind of a perovskite material has been investigated for a long time. And it was a long time ago has established an important guideline called a Goldschmidt tolerance factor, right? Which is that you want to keep this kind of perovskite structure properly. The size of the element or the ion involved has to be fitting into some kind of a criterion. Now, this tolerance vector cannot be too small or too large. There's some range you have to be. For ideal case, this t will be equal to 1, okay, for ideal perovskite. But if it's distorted, it could be 0.96 or something like that. So we based on this idea, we start to look at this so-called 214 discovered by Dr. Benoit and Mueller. And we decided there is some tolerance factor for that. And then we see, well, you want to replace some different, because I'm working on chemically. So we have to find something that proper to get the structure right. Okay, that's one thing. The other thing is that because of the experience or the result by Professor Chu showing that the pressure goes up, increase the TC and then got down. So there is some optimal value you want to achieve in terms of the size of the ion, okay? But without going into detail, but anyway, during the course, I and my student, actually, we had developed this is you see, this is original chart. We have put down something that, we have tried many elements, we placed it, okay? And we plot a figure and then they make an assumption to be properly right. So we need to find something that with the size of the ion we place, keep the copper, but changing the yttrium barium, and we use that as a mixed size. And we said, well, this line should be very ideal if we can find something that will go to that line. Okay. So this is a very simple geometry argument, not much of chemistry or really physics. Okay. But anyway, so that was the guideline, and with this guideline, we start to think what will be the next possible replacement. At that time, we already work out with the strontium replace the barium, which get a higher TC, and the calcium replace the barium and becomes TC lower and so on. Okay, and even smaller than it's not superconducting. So we said, well, okay, this is the line we want. And by looking at this chart, we said, well, why don't we just mix this yttrium and the barium? Right? If you look at this distance from here to here, almost equal to that. So essentially, you get a 1-to-1 ratio in terms of size. Then you might meet to this perfect line. Right? So we did some calculation, and that was the number we came up and said, well, let's try the composition, because in Dr. Benoit's paper, their composition is the yttrium 1.8, barium 0.2. Right? If you look at the paper. And so we say, why don't we try a little bit different, yttrium 1.2 and barium 0.8. Right? So that's how we came up, the idea. And surprisingly, we didn't make too much effort, actually, only make it 2 samples. And after measurement, and we saw this. Okay, so that was 1987, about March, end of the March. I remember March 27, and we did the measurement and showed this superconducting transition above liquid nitrogen. Okay, and that was the really exciting era when we first saw this result. And of course, right after we measured it, then we took the sample to Houston and then confirmed by using the magnetic measurement. So we published the paper and wrote the paper in a couple of days, and then sent for publication. And that's the discovery of the first superconductor about 77. Okay, so that how this the follow-up of Dr. Benoit's work, and then got to this high TC, and eventually the Raleigh follow. And we know later, very soon, about 2 months later, and then the structure was identified that this has a different, well, basically the same, still a perovskite in general, but there's a testosterone, but also some layer, the pyramid and some layer structure inside, okay? And so that was 87, and we to Houston and Alabama and Houston group, then got this the YBC work out. Okay. Well, that was a long time ago. Okay, 25 years. And during the last 25 years, many advancement has been done, achieved. Right? So there are great impact. I think you heard Dr. Benno about this technological impact, but of course scientifically, I think it's bring a lot of interesting and also important investment for the condensed matter physics community. Okay, and there are many things that the theory of matter has been seriously revised, and we know that some kind of new theory for matter may probably need to develop. Yeah, well, I don't think I have time to go through all the detail, but even we have a great challenge, okay, in this high TC research, even today. So we can still working on a new strategy for material development and processing. Actually, if you want to have a reapplication, this is very important because you can then reduce the cost of the material processing. And you need to develop a better understanding what the physics behind the observed phenomenon, and some of the property at the low temperature. You know, you especially want to have a really large current, then you need to understand better what the so-called vortex matter, and then some dimensionality related issue. There are other, I'm not going to go through the detail. But however, for the 25 years after the discovery in 1986, the community actually can say one thing, okay? There's a great triumph for physicists, chemists, and the material scientists. Because after the discovery of the high TC copper oxide, you know, for the past 25 years, many new material was discovered with the interesting superconducting property. For example, the carbon-60, and you be putting a little bit the alkaline metal, like potassium, rubidium, so on, then it becomes superconductor with a relatively high TC, okay? And the most surprising that was in 2003, I think, Professor Akimitsu in Japan, they even discovered a existing compound, the so-called diboride, you know, MgB2. Dr. Yang is one of the experts in that, you know, Professor Yang of the chairman of this particular system, and also show very interesting superconducting property with a TC around 40 Kelvin, okay? And I'm sorry, this is cobalt oxide, not the copper oxide, not the oxygen, okay? It's a cobalt O2.